session, we will continue with the Compuplast Virtual Extrusion Laboratory SpirelDie module and build on, or rather optimize, the 4-inch die that we were working on to process 150 pounds per hour of 1 MIL DPE. Now we're going to open and refresh ourselves with this project. So if we look at the results, when we set up the project, we got a good distribution at the exit of the spirals, plus or minus 4.4%. That's generally acceptable because we're going to have relaxation chamber die lips, which will further reduce this to the exit. But what we found was that inside the channel, the flow along the spiral reduced rather quickly. And this means that you'll have relatively little flow in the latter part of the channel. And we can also see this effect by looking at the leakage. We see that the leakage is very abrupt and early. So only the first half of the channel is being used. The other half is not conveying much material. So you're not being very efficient. You're not making efficient use of that channel. And if we look at the shear stress in the mandrel, we have our critical design value, which we recommend to be somewhere around 4.35 for polyethylene. And we can see that we reached this value rather early, about 24–25%, quarter of the way into the channel. We have very low shear stress. So we're going to try to correct this now. And the way we do that is we go to the mandrel and we reduce our gap. Before we do that, just notice the pressure drop here is about 312 psi, 0.31 kpsi. And this is, of course, going to go up if we make our gap smaller. So I'm going to go 0.03 and 0.10. And so I've made the gap smaller at the beginning and the end. If you'll notice that the depth of the spiral does not go to 0 here, we need to correct that. So we go to the channel. And once we click on channel, it automatically corrects that because we have this checkbox here, channel and follows mandrel surface. So now we can simply resolve this. And we see that our flow variation has increased, plus or minus 7.7%. And if we look at our flow in our channel, we see that the shear stress where the critical point is reached has moved up to about 47% along that channel. So that's better. Our distribution got a little bit worse, but we improved our shear stress condition. Now, if we look at the leakage, our leakage curve has improved. We have a bell-shaped type distribution, which is good. We're using more of our spiral channel to distribute the material, but we'd really like to have this curve brought more to the right, centered more along the length of the spiral. And so we're going to go back to our mandrel and we're going to make the geometry a little bit more complicated. We're going to leave the first little bit of the channel, let's say 20%, with a constant gap of 30 thou. That will restrict the flow here even more, and then the leakage will proceed from here. So we'll run and try that. So you can see now we've shifted the bell curve over to the right a little bit, and we have a fairly good looking distribution shape. This will appear also in the flow in the channel, but you can see it still drops somewhat early. And if we look at the shear stress, we'll see that the shear stress now drops below the critical value somewhere around 54–55%. We still have relatively high shear stress here, so one other thing we can do to keep the material in the channel is to make the channel depth a little deeper. So here we'll go from 0.5 to 0.55, and we'll run that one more time. And we see we moved it just a little bit more. We're just over 55% of the way. We still have adequate shear stress in that channel, and we have a low stress region here, but I'm not going to worry too much about this because the channel is quite shallow here. And remember, we're using an approximate solver, our control volume solver here. And I'm going to check this using our expert solver later on. But for now, I'm going to leave that. I'm not going to worry too much about this area here. I'm more worried of low shear stress in the deep sections. Now I'm just going to check our distribution here. And our flow variation now has increased to about 10, plus or minus 10%, which is a little bit higher than what we would like. So I'm going to go back to the geometry, and I'm going to modify the end of the geometry based on some experience that I have here with the program. And I'm going to put in a value here of 0.8, and I'm going to make the gap a little bit smaller. And here again 0.09. So I'm making the gap a little bit smaller, and I'm keeping the gap constant for the last 20%. I'm going to adjust the channel here, and I'm going to run the calculation one more time. Now here we see the variation improved just a little bit. Everything inside the channel stays pretty much the same, except the material leaked out a little bit sooner. So I'm going to go back and optimize now on this parameter right here. I'm going to raise this to 0.85. So I'm moving this taper up higher and solving that again. That moves that out a little further. My distribution improved 7.5. I'm going to go a little bit higher. And we're down to about 5.88, so 6%. That's generally acceptable. I'm going to try one more shot here at 0.95 and solve it again. And we see now that it got worse, so we're going to step back and go back to 0.90, and here we get an acceptable distribution, and we have our shear stress hitting our critical value above 55% of the channel, and our low values of about 2 psi near the very end. But like I say, we're going to review this once we go to our expert solver in the next session. Also in the next session, we're going to add the post-spiral sections, and we'll see how those will improve the flow variation after the distributor. So now we can exit the program, and we need to remember to save our geometry and our project. Thank you very much.